All right, it's time to begin again for the last time. We have our test on Friday, so I hope everybody's clear on what's going to happen. Everything will be on the test on Friday. The new topics are just the graph theory stuff, and then we will also have the final exam as your one last chance to catch up on everything. I'll say a little bit more about that at the end today, I think. But for now, let's get right back to it. We were talking about the traveling salesman problem, I hope you recall, and specifically the nearest neighbor algorithm. Now there is a little variation on the nearest neighbor that I want to talk about. Nearest neighbor. So just let's refresh our memories first. The idea here is you have a graph, a complete graph. That means it has edges going every which way. Every two vertices have an edge between them. I'll call them A, B, C, D like this. And the traveling salesman problem is about a weighted complete graph. Weighted means each edge has a number, weight associated to it. So this is an example. And the nearest neighbor algorithm is a way of finding a Hamilton circuit in the graph. That is a circuit which visits every vertex and comes back where it started. The nearest neighbor finds a Hamilton circuit which hopefully has a low weight, total weight. So the nearest neighbor, if I do nearest neighbor starting at A, for instance, when I ask you, say on the test or something, to do the nearest neighbor algorithm, I was going to tell you where to start. So if I wanted to do the nearest neighbor starting at A, remember this is the one where you just start somewhere and you make your choices one after another, and each time you choose the cheapest possible option. So the way that I like to do this is I'll just draw another little picture for myself. I have to start at A, and from A I have three choices, right? I could go 1, the 4, or the 5. I choose the 1. This is the idea of the nearest neighbor algorithm. You choose the cheapest legal choice in each step, where legal means you can't make a sub-circuit or a three-way intersection or something like that. So anyway, that's the first choice. Next, from B, I now have the edges from B are 1, 1, and 2, but I've already used this one, so I'm not going to do that edge again. I can either do the 1 or the 2. I do the 1 because I take the cheapest one every time. Then from here, from C, I have a 1, a 5, a 3. I can't do the 1 because I just did it. I can't do the 5 because I don't want to go back to the beginning before I hit all the vertices. I must do the 3. And then the only option from the 3 is to go back there. So my answer was A, B, C, D, A, right? Just looking at these letters in this order. And then what was the total weight that I did there? This was a 1, a 3, and a 4. So that's the total is 1 plus 3 plus 4, which is 9. All right, that's a 9. This is the nearest neighbor starting at A. Any thoughts about that? This is what we did last time. It's, in my opinion, very easy to do. One little thing that I want to discuss, and you may have noticed this on the homework if you did the homework, there is a slight variation on this called the repeated nearest neighbor algorithm, and the difference is something that I didn't mention last time, and that is it matters where you start. It matters. For example, I started at A, and I got this one. But if you start at the other ones, B or C or D, you might get different answers. So what if we start at, let's say start at C. I'm going to copy this picture down here so I don't scroll away. What if I start at C instead? So I'm going to draw my answer over here. A, B, C, D. Starting from C, where should I go? My choices are straight up for 5, diagonal for 1, across for 3. I'm going to go diagonal for 1. All right. And now from B, I'm going to go Sorry, I'm confused by my paper here. I did something differently on my paper. Whatever. From B, where should I go next? I could go either the 1 or the 2. I take the 1 across the top. That was a 1 and then a 1. Now from A, straight down would be 5, but I've already been there. I got to do this one for 4, and then across the bottom for 3. Actually, I got the same answer. This is what I realized when I was temporarily confused by my paper. This is the same answer. Same as above, right? This same pattern right there. The total would be 9. So if you start at A, you get that circuit. If you start at C, you get the same thing, although actually I would have written it differently. I would have written C, B, A, D, C. But it's really the same circuit as up there. It's just you're starting at a different spot in there, all right? What about starting at D? This is what I should have said before. This actually will be a different answer. Oops. I'm going to copy this again. So starting at D, what's it going to be? If I start at D, that's this one over here. Where should I go first? Anyone want to shout it out?
B.
Up to B. Thank you for the shout out. That's for 2, right? And then from B, I could take. Actually, at this point, there's a bit of a tie here, and when there's a tie, you can just choose at random. Now, and it does matter, unfortunately, when you make your sort of choice at random. Let's say I'm going to choose the one across the top, just for fun. So then I'll go across the top for 1. Then I have to go down the side for 5, and then across the bottom for 3. This is really different, right? This is a different answer. If you start at C, you get this kind of hourglass pattern. If you start at D, you get this box, or maybe the hourglass sideways, depending on the random choice. But actually, either way, this is your answer for this one is going to be different for this one, all right? And if I add the total up here, so this is D, B, A, C, D, and the total would be 2 plus 1 plus 5 plus 3, which is 11, all right? Which is worse than the other one. The other one was 9, okay? This is the nearest neighbor starting at different points. So the moral of the story is, so the nearest neighbor gives different answers depending on where you start, right? And, you know, starting at A might not always be the best way to do it. So if you want to use the nearest neighbor with the best possible results, you should just try it with each of the different starting points. This seems like a lot of work, but it's actually not very difficult. I mean, it's basically what I just did. I tried it at various different starting points. There's a name for that. That's called the repeated nearest neighbor algorithm. And how you do it is you choose each different starting point, and then you do the nearest neighbor for all of them. And then when you're all done, you choose the best overall. This is called the repeated nearest neighbor algorithm. It'll take you a little bit more time than just doing it once, of course, but it's not really difficult. And still much faster than doing the brute force, which is what we talked about a couple times ago. All right. So I would like for us all to try an example of that. And I want to try it with this. I had one that I handed out last time. If you were here last time, I hope you brought it. Again, I brought some new ones anyway. But it's the same one. You know, we did one example on the front, and there was the same example on the back. So I brought more in case you don't have it. I should. Anybody need one?
Thank you.
All right, so look on the back or on the front, whatever, they're the same. And I have mine also, I think. I think I have mine. Come on. This one. So what we did last time was the nearest neighbor starting at A, and it looks like that. All right. Maybe I'll just here. I'll do it. Here's the back. So what I would like to do is I'm going to do the. So what we're doing here is repeated nearest neighbor. All right. First you start at A, then you do it again starting at B, and so on. So starting at A, I find it easiest if I just. I'm not going to redraw all the lines, but starting at A, which is up here, I look at the available lines from A. I see a 1 here is the one that I want to take. So I go down here for 1. And now from D, I have a 4, the one I can't do, a 2, and a 5. The 4, the 2, and the 5, I take the 2, is like so. That was a 2. All right, and now from B, I can go straight across or down to the C. What do you say? Down to the C, I believe. And then from C, actually, my only choice, without even looking at the numbers, from here, I have to go to E and then back to A. I can't go straight to A because I can't finish the circuit before I hit all the vertices. So I got to go C to E, which is 4. E back to A, which is 7. And so this one, starting at A, is a 1 plus 1 plus 2 plus 4 plus 7. That is 15, I believe. So that, I just did it for starting at A. Now, we do the same thing, but starting at B, and then C, and then D, and then E. So you have to do this 5 times, which is a bit of a pain, but it's not really hard, I don't think. And then at the end, figure out which one is the best overall. All right? I will give you a few moments. I'll walk around maybe, see how you're doing. I'm going to do mine up here slowly. All right. Nope, not all right. No. Find it easiest to do. All right, can we talk about these? I did 3 of them up here. I hope that you got the same results as I did. So when I did A, I mean, we did this all before. This circuit is 15. When I did B, I got one which is worth 12. I hope you got the same shape here. Somebody asked me, can I just like do this in my head, or do I have to draw out the little guys each time? And I would say, no, you don't have to draw out the little guys each time if you don't want to. Although I find it easiest for me to draw the little guys out. Anyway, this one, I added up the numbers and I got a 12 for this one. I hope that you got the same thing. So this would be B, you should probably write out your answer with the letters anyway. But I'm not done, right? This is the next one. When I started at C, I got this circuit for 15. Anybody agree? I hope somebody agrees. What about D and E? So D is starting at this one here. I hope you're looking at your picture. I would go up here for 1, and then down here for 3, then up this for 1, across, and then back to there. So this is a 3 and a 4. This one is actually 12 also. It's the same shape as this one here. This is one reason why I like drawing the shapes, because then I can easily tell when some are the same as the others, where if you write out the letters, it can be less obvious. And anyway, number E looks like, so starting at E now is this one over here. I would go across this diagonal for 1, and then up here. Is that a 1? No, sorry, that's a 4. I would go straight across. Anybody agree you should go straight across first? Yeah, that was 3. And then down here for 1, and then up here for 3, and then down like that. All right. And this again is the same 12 from before. So these 3 are actually all the same answer, and the other 2 here are also the same answer, 15. All right. Anyway, my final answer is you do all of these different options, and then you choose the best one overall. And the best one overall is 12. I should write out what is the actual circuit that gives me 12. So the best one has total weight of 12. And what exactly is it? Well, you can write it, it's any one of these 3, and I don't care how you write it. Let's write it as if I started at B. So that would be B, C, A, D, E, B. I was writing out this circuit right here by the letters. All right. That, of course, is the same as this one here. Writing it with a D, it would be D, E, B, C, A, D. It's the same thing. Yeah.
Like when this happens on like a question, do you want us to write out all of them or just?
No, I don't care about that. Just one of them.
Okay.
Yeah. I mean, you can write them all if you want. All right. Excellent. This is called the repeated nearest neighbor algorithm. All right. Any thoughts about that? You should expect to see, this is one of the things on the checklist. It says repeated nearest neighbor or repeated nearest neighbor. So just an individual nearest neighbor is very easy. The repeated nearest neighbor is not hard. You just do the individual ones over and over again. All right. Excellent. And now we come to the final check on the list. The last thing that I want to talk about is a different procedure for doing this same kind of a traveling salesman problem. All right, so this one that we've been talking about last time and this time is the nearest neighbor. What I want to talk about lastly and finally is called the sorted edges procedure or the sorted edges algorithm. All right, this is another way to get good circuits in a traveling salesman problem. All right. This one does not involve a special starting point. It involves something else. It's a slightly different strategy. I thought actually I have another handout of examples for the sorted edges. I thought it might be fun to just kind of use this as a little worksheet. I know some people like the worksheets. I don't know if you like the worksheets, but here is a little thing about the sorted edges algorithm. And you should be able to just kind of fill in the blanks if you like as we go along here. Maybe that's inconvenient for those of you who like to use your computers or whatever, but we'll see how it goes. Some people don't have your fancy iPads with your $100 Apple Pencils.
Those things cost $100.
They're a lot. Are they $100? I don't know. I use the knockoff $25 that works good enough.
$100 for what?
For the pencil, I think.
For what?
Oh. For a fancier version of the knockoff, which is $30.
Wow.
Can you pass the papers down?
Oh, I'm so sorry.
All right. So the sorted edges procedure. It's the old Apple, they like to overprice their things. I have a copy of this cute little handout here with my knockoff pencil. I'm going to try and fill it in. So I'm going to try to explain, you can write this along with me, how to do the sorted edges algorithm. First of all, I will just say there's no starting point. You do this algorithm by just choosing individual edges one after another, and you don't try to make them all make a circuit. They will naturally make a circuit by the time you get to the end. But you begin with no starting point at all, and I'm going to pick individual edges as we go. But with no regard for do they connect up with one another, all right? Pick individual edges. It's not like you start here, then you go to here, then to here, then to here, then to here. It's not like that. It's you're just choosing random edges one at a time from the entire graph as a whole. All right? So you pick individual edges in order. All right? This is why it's called the sorted edges, because how you should begin is look at all of these edges overall and just sort of write them down in a big list in order. So list out the edges. Now, once you know what you're doing, you can probably do this in your head, but I'm going to write it all down. List out the edges from least to greatest weight. So what I see here is a 1 and a 1 and a 2. I see 2 3s, 2 4s. Try not to miss any. 2 5s and a 7. I think that's what we have in this picture. All right. Those are the edges from least to greatest weight. And then the way to do this is I'm going to choose which edges I want to use in my circuit. So we choose edges. one at a time, from least to greatest. And like I said before, you do not try to pick edges which go from one to the next. So for example, I'm going to begin by choosing the two ones. All right? I use both of them, one here and one here, both of them. Even though they're not touching each other, I don't care about that. I'm not trying to make a continuous path. It will naturally make a continuous circuit at the end. But you don't start off with that intention, all right? You just pick the edges, pick individual edges in order, least to greatest, all right? And as you go, you cannot choose illegal ones. So the rules about legal versus illegal are the same stuff that we talked about with Hamilton circuits. So you choose edges one at a time, least to greatest, but never make a three-way. Never make a three-way intersection of the ones that you chose. So as you're going, there may be some which become illegal. So next up is the 2. Look over here. Am I allowed to use the 2 at this point? The 2 goes like this. And I think that one is legal. If I include the 2, it does not make a three-way intersection. It also does not make a sub-circuit. I should say that here. Never make a three-way intersection or sub-circuit. Sub-circuit means finishing up your circuit before you got to every vertex. Okay, so I do choose the 2. All right, I'll circle that. Yes, I did use that one. All right, next I see 2 3s. Now, there's some issue about if there are ties, which one should I pick first? In this case, it doesn't matter. Look at this horizontal 3. Is that one legal at this point? I say no because it makes a three-way intersection at B, right? You cannot use this horizontal one, so I'm going to X out one of those 3s. What about the other 3? Is this one legal? I say no. Actually, this makes what I have so far into a circuit, but I didn't get to E yet. So this here makes a sub-circuit, and that is illegal. You are not allowed to make a circuit until you've actually gotten to every vertex. So this 3 also illegal. So you might say that first one was because of a three-way. The other one was because of a sub-circuit. All right. Now I go on to the 4s. Are either of those 4s legal? I think the one that goes E to D, so this 4 here, that is not legal because it makes a three-way. Maybe I should be Xing these out on here also, right? This 4 is not legal because it makes a three-way at D, but this 4 I think is okay, right? It does not make a three-way intersection, and it also does not make a sub-circuit. Maybe you're thinking of what about this little triangle here or this triangle here? Those don't count as sub-circuits because these are not real vertices. So that's not even a path in this graph because that's not an edge. The edge goes all the way, all right? Some people don't like what I just said. This does not count as a sub-circuit because a sub-circuit has to be a path from vertices, from this vertex to that vertex, but that's not a vertex. This graph has 5 vertices around the outside. These, what you see on the inside, are crossings of the lines, but that's not a real vertex there. So if it looks like this path is making a sub-circuit, it's not actually. All right. Did you have a question? Yeah.
Yeah, how does that work, but the 3 doesn't?
This 3 here?
Yeah.
Yeah, so that 3, if I had done it, it's kind of hard to see at this point, but if I had done that 3, I would have ended up with that, right? And the reason this is not allowed is because I made a complete circuit, but I left out one of the vertices. And that's not allowed. You have to make your complete circuit that uses every vertex. And if you ever finish your circuit too early, then, that's what a sub-circuit is. It's a circuit which is sort of too small. It doesn't include all the points. Versus here, since I use this edge, I still have not completed my circuit yet, right? Because it's still sort of open on these 2 ends. Okay, anyway, this 4. One of those 4s was not allowed, but I did use one of them, all right? Next, I consider the 5 and the other 5. This 5 is not allowed. It makes a three-way intersection at B, so that is no good. This 5 across the bottom is not allowed. This makes 2 three-way intersections, so those 5s are both illegal. I must choose the 7 as my last choice. And that's my answer, is that circuit right there. All right. So in sort of my concluding remarks, we end up with a circuit, right? Visiting every vertex. And then I can write my answer starting and ending wherever I like. So sometimes I would say, write your answer starting at A. So starting at A, it's I will follow the line. Start at A. Actually, there's 2 different ways you could go first. I could go A to E first and then around that way, or I could go A to D first and then around that way. And if I don't say so, then I don't care. Let's say A to D to B, C, E, A, right? I was just writing down that circuit in order. Starting at A, and then go to D, B to C, to E to A, all right? This is how you do the sorted edges algorithm. Any questions about that? I got 2 more for you all to try, and they are on the same paper, all right? So, come on and scroll down with me. See if you can do this one. This will involve doing the same thing. Write out the edges in order, and then choose them one by one, making sure not to make any bad life choices along the way. And then, so try this one out, and then there's another one on the back. See if you can do that one too. The one on the back is bigger. It turns out not to matter very much. Even if it's bigger, you can still do this without too much trouble. All right, try them out. We'll see how it goes. Start by choosing one of those things. same numbering, it's just a matter of.
Yeah, I was just because I have them.
Okay. Still good here?
Yeah.
Something doesn't look right about that.
You're right, that's not bad, but.
Still good here? Oh, you can flip it over and try the one on the back if you make it that far. On the back, I said find a good Hamilton circuit starting at A using the nearest neighbor algorithm and the sorted edges. So I'm asking you here to do two different things. First, do it with the nearest neighbor, and then do it with the sorted edges and see how your answers compare. No, you should use this picture so that it is down to the cell. So you go to like there is no what you wrote here. It's not, it is AC, but then it's not CD. Right. Yeah, the order that you picked them in is different from the actual order that you picked them in. Is that all right? So you began by choosing this one. Yep. You should have also chosen this one. So I'm going to label it this one. One of these would be excellent. One of them would be. So this is a one. This is a one. So you should start with those two choices. Yeah, you start with alright, yes. You start with the 2 ones, right? One here. Then 2. This 2 is okay. Right now it's 3, but that's this function. Yeah. You want to start over.
For just,
Yes.
this one can be more than, like, you can have 3 connected, right? It's not bigger.
Yeah, you can never make 3 big intersections. Still doing okay? 58. Is that the nearest neighbor? Yeah, I think that's what I got.
Okay.
I got 57.
Maybe I could have, probably would, yeah.
You okay? This, let's see, it looks like you're doing the repeating nearest neighbor. You just said the best one starting at 8. So, that's all. You're all right here? Okay. Okay.
I have a question. When I have this one and this one, can I then have this one because this is not a subscript?
That's right.
Or is it a subscript?
It's not, because that's not real vertex, it's just a
Okay.
crossing.
Is this 9, 5?
Yes.
Oh.
Mhm. can we chat about these? I know not everybody's totally finished, but for this one, the first one, I ended up getting A, B, E, D, C, A, or A, C, D, E, B, A. This is depending on if you drew it sort of clockwise or counterclockwise or something. But the edges you end up using, you begin by choosing the two ones first, and then I go on to the twos, and actually both of the twos are legal at this point. I picked this two and also this two. Some people are concerned that isn't that a subcircuit? The answer is no, that's not a subcircuit. A subcircuit has to have all three, it's not a subcircuit because that right there is not a real vertex in the graph. It's just a crossing of the lines, but it doesn't count as a vertex. So this is fine. At this point, actually, the only other legal choice at this point would be to finish it off with that guy. So this one is a 1, a 1, a 2, a 2, and a 5. All right? And then if you read that little sort of a fishy type shape as a circuit, it is A to B, E, D, C, back to A. That's this. Or if you want the other way around, if you start at A and go C, D, E, B, A, that's this one. Either answer would be fine. I hope you got that. Anybody got questions about that? Unfortunately, as you were doing this, you probably realized if you mess it up early on in the process, you're totally screwed, and you just have to start over. Hopefully you will notice if you messed it up early on. All right. Okay, let's talk about this one here. So like I said this is really two separate questions. Let's do the nearest neighbor first. So the nearest neighbor at A, that is, I'm going to start here and just take the cheapest option every time. I will leave it to you to decide which of these two options feels easier to you. I would go A to E first. Maybe I'll draw out my answer over here. I go A to E first, that's 8. And then from E now, what are my options? I can go across the bottom, 11. I got a 14, a 15, or a 14. I should go across the bottom for 11. All right, I hope this is how you did this one. This is the nearest neighbor. Now I'm over here at F. I could go straight up for 13, up diagonal for 7, or up this diagonal for 12. I'm going to take the 7. From there, I can go straight across for 1, or down here for 13. I like the 1. Come on. And then from here, my only option actually is to go across there. I can't go here because then I would finish early. So I'm going to go down there for 15. And then across here for 15 also. I hope that you got this same picture. That's what I get for my nearest neighbor. If you add those numbers up, their numbers are slightly weird, but this adds up to 57 when I did it. Anybody agree? 57? Yes. All right. Great. And if I were to write out my answer, starting at A here, in that order, it would be A, E. Oh, I started writing it up there. A, E. Then what? B. No. A, E, F, C, B, D, A. That's what I got for the nearest neighbors. All right? Everybody feeling okay about that? I hope so. And then what about, same one, let's do the sorted edges. Is this going to work? No. Let me try. Maybe it's because of this. Come on now. They don't like copying things that are from the background. Oh, I did it. All right. This time, so I said before, the sorted edges thing, it is kind of a pain to write down all of the numbers in order. But actually, you can just kind of look at the graph and do this more or less in your head. Although maybe I'll write them down. It's a 1, and then the next would be a 7, a 8, a 9. I see a 10. I see a 11. Is there a 12 in there?
Yeah.
1 12, 2 13s. There's a 14 and 2 15s. 3 15s. 2 14s? All right. I'm so fortunate to have you all. I think that's it. All right. And now I choose them in order.
20.
There's a 20?
Yep.
Oh, yeah. I was shocked. A 20? But hopefully I won't have to use the 20. All right, I begin with the 1. Okay, the 1 is definitely legal as my first choice. Next, the 7. I take the 7. Next, the 8. Anybody say, is the 8 okay here? Show me the thumbs. The thumbs are up. The 8 is okay. Okay by me. Next is the 9. This 9 here. Can I do that one? The answer is still thumbs up. Yes, you can do this 9 here. You may feel badly about making a subcircuit. Remember, that does not count as a subcircuit because this right here does not count as a vertex. Next would be the 10. I believe the 10 is not allowed here. That makes a 3-way here. It also makes this sort of trapezoid type subcircuit no good. The 11? Also not allowed. That makes a 3-way at the F. The 12. The 12 makes a 3-way at the F also. This one is also not allowed. The 13. There's a few 13s. That one makes a 3-way at C. This one makes a 3-way at F. So, can't do either one. 14s. This 14 from D to E looks good to me, right? Yes?
I have a question there. It depends on which 14 you choose first. One of them is possible and the other is not.
Yes.
But when you draw this one first, the other one is not possible, and the other way around. Which one?
Now, the other one is never possible because if I decided to choose this, that's a subcircuit, which doesn't include D. So that's not allowed. Yeah. It is in theory possible that there will be like an ambiguous choice and you just have to guess at random, but on our test I'm going to make it so that that doesn't happen. So I choose this 14, not the other one, and I finish with this 15. So I picked one of the 14s and one of the 15s. All right. I hope you got the same, you should have gotten the same picture over here. Now if I want to write this answer down starting at A, which is down here, I now just look around as I go around this thing. I go A to F to C, so A, F, C, B, D, E, A. I'm just reading the letters as I go around this path. Or you could have written the other way around, A, E, D, B, C, F, A. Those are both correct answers. I don't care which one. And this one, when I added these numbers up, I got, whoa.
No, it doesn't start at A. It starts at the 1, doesn't it?
The answer is this circuit here. You can write, when you write the letters down, you can start wherever you like. Yeah, it's true. The first edge that I chose was this one, which was not near A, but it doesn't matter. Okay, and this one, I added these numbers up. I got 54. So in this particular example, the sorted edges worked better in terms of it gave me a better answer. But that's not always a guarantee. They're just two different ways of doing the same thing. All right. Any thoughts or feelings about that? This is the sorted edges. All right, and that's all that I have for us. Maybe I thought we should talk just for a few moments about the test, but I don't have any more new material to go over. It's been a pleasure. Let's talk about the final exam. Any remaining things to say about this? Yeah?
Not for this, but for the test on Friday, like what number is it going to go up?
Yeah, so that's what I'm gonna tell you in detail. I am looking at my checklist right now. The test on Friday. So first of all, the test on Friday and the final exam are basically the same. They're not the same exact questions, but they will cover the same amount of material. The final exam is just meant as one final chance to get all of your checks in a row. But anyway, our last test, of course, will include all of the old material, but the new topics are basically just the graph theory topics on the checklist. This is D1 through D11, and there will be no D12 or D13. Those are on the list, but if we had one more day of class, we would have done them. But I decided not to try to squeeze them in the next 20 minutes. So those you should just remove from your checklist entirely. There will be no questions about that. You don't even know what it means, so those are not on the test. But maybe I'll just say out loud what they are, and I'll just refresh your memory. D1 is just about paths, degrees, connectedness. This will be like very basic questions about what the degree of a point is. I'm not going to ask you definitions, but I'll show you a graph, maybe say, tell me what all these degrees are. I'll ask you if it's connected or not, and some basic things about paths. Yeah,
So we did D10 and D11 today? Not like,
that's right.
okay.
Yeah, right. So D1 is just about degrees connectedness. D2 is about imagine a graph and answer basic questions about it. There were similar questions on the homework last time. I might say something like, imagine a graph where the vertices are all the presidents of the United States, and they have an edge between them if one of them, if they were, I don't know, within 3 inches of height with one another, or something like that, and then ask you some questions about that kind of thing. Next, D3 is the formal description of a graph. This is very easy if you remember what it's about. That's just looking at a graph and writing it down as a set of vertices and a set of edges, which are pairs, or going the other way around. I show you a set of vertices and edges, and you draw the graph for it. That is very easy if you know what you're doing. Next one, D4, is also very easy. Does an Euler circuit or Euler path exist? You have to remember the rule. Euler circuit exists if all the degrees are even, and an Euler path exists if there are 2 odds and the rest are even. Next one, Euler's sum of degrees theorem. This is a strange one. The sum of degrees theorem says the sum of all the degrees in every graph has to be even. And you can demonstrate that certain real-world scenarios are impossible, like there was a homework problem about me and my friends, Chuck and Patty and Tony and Aaron and Sean, I believe, were the people. Those are real people. That was about the sum of degrees theorem. I hope that one made sense. D6 is draw in an Euler circuit or an Euler path. That's something, you make the little line go around with the arrows on it. Number D7 was draw in a minimum duplication circuit. This is a little bit more complicated. You have to decide first which edges you're going to duplicate and then draw it in. Actually, I was grading the homework on that just this morning, and I noticed a lot of people didn't seal the deal. They told me which edges they would duplicate, but then didn't actually draw in the minimum duplication circuit. If I say draw the circuit, you've got to actually draw in the circuit. Don't just tell me where the duplications would be. That's not the answer. Next, draw a Hamilton circuit or say that none exists. This is like on the homework for tomorrow. And then the last 3 were traveling salesman. The brute force, which is when you list out all the possibilities and just check them all. Then the nearest neighbor and the sorted edges. So that's about it. Anybody have any vague questions about that? Our homework is due tomorrow. We got 20 more minutes on the clock. I'll hang around and talk about, if any of you do have questions, review things, I'd be happy to talk about it. Otherwise, I'll see you on Friday.